It's Rachel. I'm with Simuli, and I think I've got some slides. Can I just hit space? What do we do? Yay! There they are. Okay, so at Simuli, what we're working on is this pipeline to reinvent how data lives and moves, right? And we think that is kind of the correct action for getting better, more scalable AI. So one of the issues that we have today in AI is that anytime you want your model to be smarter, you think about scaling, and the word scaling really just means two things, which is what saddens me, which is what at Simuli we're trying to change. Scaling means that you either throw away information by doing some crazy amount of data pre-processing, right? You do PCA, things like that, or you just plug in more GPUs. You add more data and you plug in more GPUs. And that's neither good for the environment because the amount of power that these NVIDIA chips use is exorbitant. Neither is it kind of what biology does, right? So you probably saw on the post that we're going to take some lessons from other cognitive architectures. That's going to be the biological ones. And I want to challenge you guys because there is a framing, a philosophy in deep learning which says features have to be constructed by propagating signals, some sort of error signal metric, all the way down through the layers to create these rich features. And that feature engineering is really what makes these AI models work. And while that's true for a lot of the current deep learning models out there, it's not the only paradigm. It's not the only paradigm we see in some of these Markov models and reinforcement learning, right? It's not the only paradigm we see in genetic algorithms, which can do anything deep learning can do. It just takes, 100 years longer, right? But there's these other paradigms, and what we're going to show you is that in biology, this is actually the dominating paradigm, is that feature engineering is not what it's focused on. In fact, we don't even care how your features come. You can make them at random. What we actually care about is how you use these features. How do you look at these features? What operations do you do? So our really brilliant colleague, Peter Suter, is going to speak next, and he'll get into what it means to move features around a hyperdimensional space, right? But for now, I'm going to talk at a high level about some fun stuff. So that's what we do. That's what we're doing. Ultimately, we want to walk towards this AGI, artificial general intelligence, not adjusted gross income. it's the artificial general intelligence. We want something that wants to help us, right? Just how we all rely on each other to help each other, right? We want something that can go beyond ourselves to help all of us in ways that we can't even imagine today. So that being said, our kind of magnum opus, our baby and our passion is what we call ReArc. And it's a new framework. It's a new cognitive framework. It hasn't been done before. And it comes from something called the recommendation architecture, which what we've done is we've taken this very nice scientist, Andrew Coward, who's at the Australian National University. And what we've done is we've taken his work, which is a theory of how understanding cognition, higher cognition, in terms of anatomy and physiology. I said that very slowly so people can really let that sink in. His theory is for understanding what goes on in our brains in terms of anatomy and physiology. He's not doing this, right? He is an advisor on our team. But what we've done is we've taken his first principles and we've said, what is the best math? What's the best way to engineer this? So I just want to make that distinction. So this theory of neuroscience and how higher cognition works, it hasn't been debunked. There hasn't been any sort of counter support. That doesn't mean there won't be. If you find some, please tell me. I've been looking for 3 years. Please come tell me. So really what ReArc affords is the first thing that's most important is 2 new learning algorithms. And these 2 new learning algorithms are really going to help everyone scale up their AI. So our goal is to take what we can from our new cognitive framework, ReArc, and make it available to anybody's AI that they're currently using. Now, there's going to be a couple caveats, like you need horizontal and vertical hierarchies, right? You need to separate your consequence feedback, something like your reward-based learning paradigms, from your actual feature engineering, which I was harping on earlier. But these two new learning algorithms we're going to talk about a lot today, which is receptive field expansion and indirect activation. Receptive field expansion allows you to do one thing, right? It allows you to learn new things without forgetting old things. And indirect activation allows you to bootstrap a priori knowledge. So I think I have some slides later where we'll jump more into that. If not, then I'll just talk without slides. So basically these two new learning algorithms, they're an alternative to backpropagation. You don't need to use backpropagation. We still use backpropagation. It's a good algorithm, and it's very useful in some parts of our model. We have a modular ReArc system. One thing that's very important that we found in cognitive architecture is for keeping resources low, because we're talking about scaling, so we're going to be talking a lot about resource management, is about keeping things modular. Right? You have dedicated centers that can cross-share resources, right? Neurons, information. But one of the issues in deep learning today is this autograd SGD. So stochastic gradient descent, you've probably heard, is the #1 algorithm that helps tune the weights of a neural network so that it can learn better weights to predict the correct answer, right? The mechanism that's often used to implement stochastic gradient descent is called autograd, which is the partial derivative in calculus that we take, which is why NVIDIA GPUs are really good at doing this, because they work as a SIMD architecture, which means same instruction, which is this partial derivative over multiple pieces of data, right? So we need to get away from that, right? Brain is not SIMD, SIMD in some parts, right? But it's MIMD. There's many instructions going on. There's many different things going on in your brain at once. It's not all optimized for this one partial derivative of calculus, right? So that's important. And another thing that we want to add here is this working memory. And anyone who works in transformer space is just yelling at me in their seat right now. They're like, we already have attention mechanisms. Yeah, attention is good, but you need this attention to tap into long-term contextual memory, right? Otherwise, you basically have that girl from 50 First Dates, right? Drew Barrymore. We need to be able to have this kind of, what am I thinking of now? Because what input am I being gathered? I'm looking at all of you, you're looking at all of me. But I also have a long-term memory that's kind of spawning up my years of my PhD that helped me create some of these ideas and put this stuff together, right? So I can't just have one, otherwise I'm gonna overfit and just tell you guys whatever you wanna hear, right? This is where you get mode collapse. Okay, I hope I'm not kind of going too fast. Multimodal really jumps out at us for ReArc, because when you have multiple dedicated modules, which are sharing fundamental resources, which in the brain are neurons, but in our models you'll see, which can be various things. They can be kind of these long vectors, such as in transformers. They can be whole entire matrices, geometric shapes, anything, whatever your information holding unit is. If you allow that to transfer across dedicated modules in a cognitive architecture, you get something that can be very multimodal when you have things like being able to learn new things without forgetting old things, right? When you have this thing, you can get down to this thing, right? And obviously it needs to be modular. Didn't really write those in order. Okay. So what we're hoping to get out of this is fewer computations. I actually have a paper that shows this, right? Shows that we actually do fewer computations when you set up your cognitive architecture this way. Considerably fewer. All right, we'll jump into the paper details. More remembering. What does more remembering mean? That means if I learn task A, and then I learn task B, and then I go back to task A, that I should perform equally as well on the first task after I learn the second task. And this is a huge pitfall of AI right now, right? Siri in your phone, she's built on something called an LSTM, a long short-term memory model, right? And also Siri, this LSTM, not Siri, but LSTMs have been known to be very good at trading certain stocks in a regulated pattern, right? I'm not saying set them loose on the stock market. You should do a little bit more than that. But basically, if you take Siri and you tell her, go trade, Microsoft stock for me, she will forget everything she knows about language. So then when you go to ask Siri, come back to me and talk to me and be my glorified alarm clock, then Siri's gonna be like, I don't know how to do that anymore because she can't speak English, but she'll be good at trading. So that's an example of task A to task B to task A, which is total failure in today's in models, right? So that's something that we're looking for. And we want something that's human similar. And this is a philosophy, right? This is something that is Simuli. We want something human similar because one, I want something that I can understand and understands this world similar to how I understand it. Otherwise, I don't know how we're going to talk very well, right? I don't know how I'm going to share my problems with this thing if it doesn't understand the world in the same way I do. If you've ever seen that movie Arrival and the depths of language, right? And then obviously understanding value learning and autonomy comes with something that might be human similar. So I'll leave the philosophy for another day. If you want to read the full paper of kind of the work that I'm going to be sharing on our ReArc model, this is the title of the paper. It was published in a consciousness journal. So I would take the consciousness stuff as the consciousness stuff, and I would take the model stuff as the model stuff, right? Okay. And this work was done with Dr. Susan Schneider, which Dan mentioned. Thank you, Dan. And Andrew Coward, who is our beloved advisor who came up with the recommendation engine principle architecture. Okay, so let's get into a little bit of the meat of this. I'm going to have to point at stuff. So normally, in the regular kind of deep learning, the way we do things is what we see in this top box here, right? This is backpropagation, reinforcement learning. These are kind of the two driving algorithms. Backpropagation really isn't the correct term, right? We're talking autograd backpropagation. But bear with me. So you have some layer of neurons, right? And what you're going to do is you're going to tune those, or you start them at random. However you figure out, you get some prediction. And that prediction is going to be your behavior. Right, so if you're dealing with robotics, like the Boston Dynamics robot dogs, it might say do a bark, right? Predict that the correct thing to do right now is to bark. And then it does a bark, and then its human operator says, no, bark was not a good answer. And so you get a consequence feedback signal, right? This is how we train a lot of children in school. This is very classic psychology stuff, right? But what happens now is this consequence feedback signal in red propagates through all the layers of the neurons. So all of the features that were learned that prompted the model to choose an action, whatever they had learned previously, have now all gotten pushed to learn the current task. So this is what we call catastrophic forgetting, right? And sometimes it's not so catastrophic, but sometimes if you want multimodal learning, if you want things that can scale, it is catastrophic because you've tuned all of the weights for the sake of the current task. And it will always continue to tune for the sake of the current task. So you'll always be leaving information you learned previously. Okay, so the way we do it in the RA model is we model things from human brain, right? And we don't take our modeling so seriously, right? We're doing first principles. So what we do is we have our cortical neurons, which is just a part of the system that learns features. Okay, so we have our feature learning neurons. And then we have our neurons which learn how to interpret features. And I'm not going to go over all the fun brain names for you. You can read there. So there's two things that we've separated out here. It's very important for cognitive architectures. And this is what you see in all of biology, all the way even birds, and in some reptiles, right? Reptiles that have small, tiny cortexes. But basically, you separate out things that define features and things that interpret those features. So for everyone who's staring at me like I have no idea what she's saying, I'll give a brief little analogy, right? So if you had an artist who had painted an abstract painting, right? That abstract painting is like your feature. And then someone goes up in an art museum and looks at that abstract painting and they go, oh, I think the artist was mad when he painted this because I see strokes of yellow and red. And the artist just happens to be right behind them. And the artist says, no, this is what it means to be whimsical, right? That is the difference here, right? So you still have a consequence feedback signal. You still have the artist really, like someone coming and saying, no, your interpretation of what the features were and what to do with your interpretation was incorrect. So instead, you learn how to interpret. You learn how to interpret arbitrary feature space. And that was the whole key earlier that I was talking about as a paradigm shift from traditional deep learning. right? But what you'll see is when you do that, you don't have to spend so much energy feature engineering and so much resources feature engineering, which is the data-heavy, resource cost-heavy part of a lot of these models. You can focus on interpretation, which is a lot cheaper. And scales, we think, remains to be provably tested. We think will scale much better. So, all right. This is what our architecture looks like, and we're borrowing brain names, okay, names from the brain. We don't really call it this, but it's quite a large architecture. I mean, it's a brand new cognitive architecture. It'd be like diving into ChatGPT's brain and sorting through everything. So these boxes with easily accessible names is a lot easier. So basically, in the paper that I'm going to show you, what we've done is we've had an algorithm act directly on the inputs to do what we call a binding effect, if anyone's a vision scientist in here. And then we have this hippocampus, which runs part of the two new learning algorithms I talked about, RFE and IA, which acts directly on the feature space that is encoded from the inputs, which have been modulated by the binding algorithm, which we call the thalamus. And then these things at this point on this half, that's your feature space that you've now learned. And on the right, well, you don't really learn them, but you know, they come in there and they get sorted out automatically. And then on this half of the graph, you learn how to interpret that feature space with your BG, and you get your outputs, right? Okay, hopefully that's somewhat clear. Alrighty, okay. So basically what we see, and I'm not going to go too much in depth because I want to leave a lot of fun time for my colleague to show you guys math equations. I know everyone's there. No, it's going to be fun. So what we see is we have three tables here, right? So the first table is showing you the number of learnable parameters. So in a regular neural network, a learnable parameter is a model weight. Okay, and we use a similar analogy in our ReArc model for what is a model weight. So you can see the RA model has way fewer learnable parameters than something called a DQN, which is a deep Q network, which is still very popular and used today, although it is not a transformer. And then we compared that to something called ResNet. So ResNet, I think, has a UNet architecture. No, DQN has a UNet architecture. And then ResNet has these skipped connections. So ResNet does this kind of forward propagating of information, which is supposed to have it keep long-term contextual working memory, right? And then we show the number of training iterations. So training iterations is how long it takes for you to go through the task, update the model weights, until you get to a certain accuracy. So each of these, first table 1 and table 2, is like to get to a 77% accuracy on the task or to get to a 90% accuracy on the task. And the task that we did is kind of a strange one because we are just starting to work with this model and we haven't quite fit an IO stream on it yet. And so basically, I'm gonna explain this very casually. You have a sine wave. Everyone knows what a sine wave is? It goes like this, right? And let's say you at random take a cookie cutter and you cut out this sine wave. And that's one set of data. Now you modulate this sine wave, so it's a little bit different, multiply it by a constant or whatever. Then you take a different random cookie cutter. Then you do the same thing over and over again. So every input you get, you're trying to say, is it from an original sine wave or is it from one of the 1 through 30 modulated sine waves, okay? So you're basically doing classification of whether or not this part of data belongs to which sine wave. And the reason we did it this way is so that every single input is brand new. It's never been seen before. So in traditional deep learning, what you do is you train on the same data set thousands of times, and then you go on a test set. We do it different. We say every time you get new information, you never see the same thing twice. Because in reality, you never see the same thing twice, right? The way photons hit your eye, the way your retina captures the light, things are slightly different every single time. Right? You'll never be in the same situation twice, ever. Every second's different. Okay, so anyways, we show that it's more efficient. Right? We show that it uses less learning parameters, uses less training iterations, And if you multiply parameters times iterations, that is a vague proxy. I'll allow you, it's a vague proxy for how much computation this model is using, right? Because that essentially is the bulk of the computation. We also measure the megabytes of RAM to run these models, although I'll tell you it's not the most fair comparison because there's a few confounding variables. So the measure proxy here of parameters times iterations, I think, is the biggest, kind of most stark result that we had, because you can tell it's quite a big difference. So task 3 is exactly what we were talking about when we were talking about training task A, task B, task A. Task A, task B, task A. How well do you do on task A, right? Okay. So I'm going to skip this. You can read the paper and go over it for the sake of time. Basically, we tried different methods of consequence feedback to tell, do I have to tell you the right answer or just have to tell you that you're right or wrong, right? It's kind of like if anyone has children, sometimes when they're learning, it's best not just be like, no, the answer is A, It doesn't really help sometimes. Sometimes you want to say, no, that's not right. Do you want to think of a different answer? Give them a second chance. How quickly can they learn from getting a second chance? So we did the same thing. Okay, so this is where Simuli is out, right? We've translated our model. It was in small talk. I just want to know, has anyone heard of the language small talk? Raise your hand. Wow, this is the biggest amount of people I've ever seen in any room raise their hand for small talk. Oh, I'm sorry, but we put it in Python instead of small talk because I know small talk is better for it, but anyways, it's in Python now. Anyway, so that was our translation feat. And right now what we're doing is we're fitting a new input-output module so we can do things like MNIST and, robotics, anything instead of just sine waves. Then we'll do our model build out, which we have to put in some things like learning, autonomy, emotion. There's a couple feature build out spaces. And then we'll get some people, some of our hardware partners or ourselves to make this run fast on chips. And then obviously we'll test it before we give it to the world to make sure it's safe. And then we'll have a party because it's going to be awesome. So kind of what I'm trying to show you is that scaling starts not only with the cognitive architecture, which we talked a little bit about, right? But scaling also starts with input-output, because my whole kind of key message here is that if you have this thing that stores your information resources, that's able to transfer itself between modular parts, then you really have something that can start being more resource efficient. And so you really need to think about what is that thing that is going to store and move the information. Is it going to be neurons? Is it going to be matrices? What is it going to be, right? And so Peter will talk about this thing called hypervector, which we really like. We love hypervectors at Simuli. They're our best friends. But that's really where we think the first opportunity for setting up the foundation of scaling is appropriate. And I'm leading you all to say this because what we're building before we really build ReArc is this thing called nebulae compression. So we're very close to launching a new compression algorithm that's data agnostic and verifiably lossless. And it puts all of our data in a standardized format. It is a one-step preprocessor, which is kind of a big deal. Because what you've done now is you've done the same thing the brain does is when it makes neurons, right? It says all information is going to live in terms of a spike. Did it spike or not, right? And we're going to say all of our information is going to live in something like a hypervector. And there's a lot of nuances. We could have another 6-hour talk on what I just said. But the whole goal here is that if you can compress information, you can learn something. So a lot of people might be familiar with Marcus Hooter's AIXI paradigm. He has something called the Hooter Prize. It's a compression prize. It's a very interesting body of literature. We're quite aligned with that body of literature that if you can compress something, that you have learned something about it. And if that compression happens to standardize and format all of your data into a compact vehicle to move information, then that's something that's really useful for this resource management cognitive paradigm that we've been talking about, right? And then phase 2 is that, wouldn't it be nice if we didn't have to uncompress our data before we computed it, right? So that's our AI kind of API that we're working on in the background. So kind of our bread and butter is Simuli allows us to facilitate this new AGI research avenue cognitive framework called ReArc, right? So compression, how do you compute uncompressed data, put that in a pretty cognitive model, bootstrap our new learning algorithms, and bam, I think you'll have something that's way more efficient, way more powerful than what we see today. So I think it would be good, this is my cat, thank you guys for listening. It'd be good to take some questions probably because I went a bit fast and I left some things out. Dan, how much time do we have, Dan? How much time do we have?
You got like 2 minutes.
2 minutes.
Just use this.
Just use this. Dan doesn't like me with the microphone.
Does anyone have questions? All right. Just.
Yeah. Do you train everything at the same time, or do you train it separately, for separate?
Yeah.
Sure it doesn't work.
No. Is this working? Yeah. No, that's a very good question. You can train. So we call this. I don't want to bore you guys with jargon, but we call this condition, detection, and definition. So you have a condition. Let's define it. That's what makes it a condition, that you defined as a condition. And you need to detect it. This is my cat. I see a cat, right? Conditioned cat, it's detected, there he is, right? So that's what we call a CDD. And the CDD is this general feature space that I was talking about, right? That would be your cortex. And then everything else, which is your behavioral selection, which is how do you interpret, how do you choose what the cortex is trying to, like, cortex looks like this, what am I going to predict to do? We call that the behavioral selection, or BS, right? Which is a funny acronym. But so anyway, so you can train your CDD and your BS can be totally separate, and they have a communication bridge through them. So if you go back to one of my pretty diagram that had all those brain terms on it, there's like the SINR, those pathways help mitigate the connected to. But yeah, you can train them separate.
Okay.
Or you can train one separate.
Let's do Peter's talk, and then
Okay.
I know a lot of we have Yoshabak later, but
He'll be here. He's
yet.
coming.
So let's do Peter's talk, and then we'll just do questions until Yasha arrives. So